This is the second part of our lecture on lattice vibrations in a one-dimensional diatomic chain. In the first part, we derived the dispersion relation of a diatomic linear chain under longitudinal vibrations. In this video, we will plot the dispersion relation for a linear diatomic chain of atoms and give you a step-by-step explanation of the variation in dispersion profile at various k values and its physical inferences. Contrary to a monoatomic chain, you will see that in case of a diatomic chain, there exist two separate branches, the acoustical branch and the optical branch. I will also explain that there exists a band of frequencies between the two branches for which the lattice vibrations are completely ceased. This branch is called the forbidden band. If you go through the entire video, you will be able to visualize the type of acoustical and optical vibrations, both longitudinal and transverse, that can be generated within the diatomic chain for different k values. So let us start. This is how we defined a diatomic chain in the first part. If you remember, we raised certain questions. Following are the questions. If you have not gone through the first part of the lecture, I would advise you to do so. The first question is, will the dispersion relation change in the case of a diatomic chain of atoms if you compare it with the one you got for a monoatomic chain? So the answer is yes. We have seen there is a significant change in the dispersion relation. One such change was in the case of a diatomic chain, for one k value, we can have two possible omega values. The second question is, what is the dispersion relation in the case of a diatomic chain of atoms? So we had derived the dispersion relation of a diatomic linear chain of atoms in the first part. We will answer the third and the fourth question in this part. The third question is how the range of frequencies or the frequency spectrum of lattice waves propagating through this solid is getting affected. We want to know what range of frequencies of waves propagate through such solid, or what are the range of frequencies in which the atoms within the solid can vibrate. The fourth question is how this frequency range depends on the elastic properties of the solid. In fact, not only on the elastic properties, but on other structural parameters like the mass of the atoms and the lattice parameters. Now, many students may need to remember the steps involved in the derivation of the dispersion relation from exam point of view. The derivation is simple but lengthy. You may forget some of the steps after some time. The best practice would be to pen down the derivation once or twice while going through the first part of the lecture. You can also divide the derivation into small steps. All you need to keep track of these steps and you are done. I tried to divide the derivation in the following steps like this. The first step would be to define the system. You establish the nature of the system and define the components or the parameters involved in the system. Then you identify the repeating units. You recognize the recurring structural units. In this case, there are two such units. Then you write the force equation for each unit. In this case, the forces involved are spring forces and the resulting force equations are second order differential equations. Then you write the periodic solution of these second order differential equations. Then you put or substitute the solution back into the differential equation. Doing so, you identify a set of linear homogeneous equation in terms of unknown parameters. In this case, the unknown parameters are capital A and capital B, which are nothing but the vibrational amplitudes of the two atoms in the diatomic chain. You have to express these vibrational amplitudes in terms of known parameters, and the known parameters are small m, that is the mass of the smaller atom, capital M, the mass of the heavier atom, small a, that is the lattice parameter, beta, that is the spring constant. Then you solve the linear homogeneous equations, and in order to solve it, you make a determinant of the coefficients of capital A and capital B and equate it to 0. Doing so, you will identify a relation between omega and k. So you establish the relation between the frequency and wave number. Now this relation would be a relation in terms of known parameters, that is small m, capital M, A and beta. The relation in this case is a quadratic equation of omega. You have to find the roots of the equation, and finally you formulate the dispersion relation. So if you remember these steps, you can derive this dispersion relation at any point of time. So proceeding further with our discussion, for a diatomic chain like this, we get the dispersion relation as this, whereas for a similar monoatomic chain like this, we have the dispersion relation as this. Now, if you see, the dispersion relation of a diatomic chain has two components. One is omega plus, the other one is omega minus. So, omega plus, if we restrict only to the positive sign, and omega minus when we restrict only to the negative sign. This is the omega versus k plot of a monoatomic chain, while this is the omega versus k plot of a diatomic chain. It can be seen that for a monoatomic chain, for one value of k, we have one value of omega. Whereas in case of a diatomic chain, for one value of k, we have two different values of omega. This is the omega plus value and this one is the omega minus value. In other words, we can say that in a monoatomic chain, there exists only one allowed frequency range of propagation, which depends on the structural parameters like m, beta, and the lattice parameter a. However, in a diatomic chain, the allowed frequency range of propagation is split into two branches. The upper branch, which is determined by omega plus, is called the optical branch, and the lower branch, represented by or determined by omega minus, is called the acoustic branch. In both the chains, the pattern repeats within a certain range of k values. For example, in a monoatomic chain, the plot which lies in the range minus pi by a to plus pi by a is repeated. This range is called the first Brillouin zone, and the boundaries of this range are called the Bragg planes. The range between minus pi by a and minus 2 pi by a and pi by a and 2 pi by a is the second Brillouin zone. The features of the plot in the first Brillouin zone is repeated in the second and in subsequent zones. Similarly, in the diatomic chain, the plot which lies within the range minus pi by 2a to pi by 2a, this pattern is repeated at subsequent Brillouin zones. So this range is termed as the first Brillouin zone, where these boundaries at k values minus pi by 2a and pi by 2a are termed as Bragg planes. Here also, the range beyond these, that is from minus pi by a to minus pi by 2a and pi by 2a to pi by a, or is the second Brillouin zone. The features of the plot in the first is repeated in the second Brillouin zone, and so on. This is the enlarged view of the plot of the dispersion relation for a one-dimensional diatomic chain of atoms. We will now evaluate the plot within the first Brillouin zone, that is within this range, as the features are repeated in subsequent zones. The plot of the dispersion relation within one Brillouin zone is plotted over here. And this is the dispersion relation for a diatomic linear chain of atoms. Now let us consider the case k tends to 0 or is almost 0. That is, k is very small. We know that k is 2 pi by lambda. Thus, when k tends to 0, lambda tends to infinity. That means we are talking about very high wavelengths. So under the limiting case of k tending to 0, sine of Ka is 0, which means that this term will become 0 in this case. So we are left up with this term. So there will be two expressions for omega. One will be omega plus, keeping this sign only plus, and the other one will be omega minus, keeping this as omega minus. So you can see that omega minus will be this, and this can be taken out from the root sign, and both the terms will be similar. So this term and this term cancels, and finally we get omega minus to be equal to 0. So this suggests that both the phase velocity and the group velocity is 0. Now we'll get an expression for omega plus as this. So since this is the positive sign, so they both gets added up, and this is the final expression for omega plus, which is a non-zero value. So in the plot, if you see, this is omega minus, omega plus will be this one. Now we know the phase velocity in this case will be omega plus by k. Since omega is finite, this value will also be a finite value, and if you put the value of omega plus from this expression here, we get it to be 1 by k, and we can write it as under root 2 beta by mu, where mu is the reduced mass, and the reduced mass is expressed as 1 divided by 1 by m plus 1 by capital M. From our earlier derivation for a linear monoatomic chain, we know that root of beta by mu is Vs by A. So we can write Vp, the phase velocity, as root 2, the root 2 we are getting it from here, divided by k times Vs by A. Now the group velocity, which is the derivative of omega plus with respect to k, is this one. Since this term do not involve any k value, the derivative of omega plus with respect to k will be 0 because this term will be constant with respect to k, as a result of which the group velocity is 0. What does it mean? This suggests that the individual atoms vibrate. Now this value, since we are dividing it with a very small value of k, this value will be very large. So there will be a high frequency vibrations of individual atoms. So the individual atoms vibrate here, but there is no net transfer of energy by the resulting wave packet, which is formed by the superposition of these waves. Such a wave is considered to be a stationary wave. Now consider the region where k is small, not small enough that it will be neglected. In such a condition, sin Ka will not be 0 as in the limiting case, rather it will be roughly equal to Ka. So we are talking about this region where k is small on both sides of the origin. So under such a condition, if we replace sin square Ka from the dispersion relation expression as k square a square, we can write the expression of omega minus by retaining only the negative sign here, and the expression would look like this. I can take this expression common by bringing it out of the root sign. So I can write it like this. Now this factor, one of these factors from the bracketed term cancels. So we are left up with this term. So we can write this expression as this. Now again, I can take this factor out from the root sign. So I can write it like this. In place of this, I am writing it 1 and then minus root over 1 minus small m capital M divided by small m plus capital M whole square times 4 into k square times a square. Now if I expand this binomially, I get an expression like this. Ignoring the higher order terms, I can, and obviously this one and this one will cancel. This minus and this minus makes it positive. So I get the expression as this. I can bring this back into the root sign. So the expression takes the form like this. This small m capital M cancels with this small m capital M. One of the m plus capital M factor gets cancelled. So we are left up with this term. If you compare it with the expression with the straight line equation y equal to mx plus c, you can see that c is 0 here and the slope m is root over 2 beta by small m plus capital M times a. So in this region, omega minus k curve resembles a straight line. This suggests that the phase velocity, which is omega by k, and the group velocity, which is d omega by dk, are same in this region where k is small. Now considering the case of omega plus, which we could get by retaining the positive sign here in the dispersion relation, and for this case we replace sin square k as k square a square, then omega plus can be expressed as this. Now again, taking this expression out from the root sign, we get this. Here also this factor cancels, so we are left up with small m capital M. I can take beta times 1 by small m plus 1 by capital M out or common. So I am left up with this term. If I take this term common, this becomes 1 plus the rest of the term. If I expand this term binomially, we get this. Ignoring the higher order terms, this 1 plus this 1 now no more cancels, rather it becomes 2, so it becomes 2 here. So now you can see this expression for omega plus is not a linear equation. Hence the omega plus versus k curve in the region where k is small, that is in this region, is not linear. This suggests that the phase velocity and the group velocity of the resulting waves are not same. Consider another case when k is plus minus pi by 2a. So we are talking about these ends, which are represented by these dotted lines. So here it is minus pi by k axis is minus pi by 2a, and here the k value is plus pi by 2a. When k is plus minus pi by 2a, then sin ka would be sine of plus minus pi by 2a times a. So this a cancels, and this will be plus minus sine of pi by 2, which is equal to plus minus 1. Hence when k is plus minus pi by 2a, sin k a is plus minus 1. Squaring, we get sin square k to be equal to 1, which means that under such a case, we can replace this bracketed term as 4 by small m times capital M. Thus, omega plus takes the form, if we retain only the positive sign in this dispersion relation, we get the expression for omega plus, and under such a condition, we put sin square k equal to 1. So we are left up with this term for omega plus. Now if you look into this term, this is nothing but 1 by small m minus 1 by capital M whole square. Now this term can be taken out of the square root sign. So we are left up with this term. Now this is positive, this is negative. So beta by small capital M cancels. So omega plus comes out to be 2 beta root over 2 beta by small m. You can see that omega plus is independent of k, which means that d omega plus by dk in this case will be equal to 0. Now looking into omega minus term, which we can get by retaining the negative sign in this dispersion relation. Under such a case, omega minus will be, we retain the minus sign here, and this becomes 4 by small m times capital M. This term is nothing but 1 by m small m minus 1 by capital M. Now since this is negative, here the small m term will cancel and we are left up with 2 beta by capital M. So omega minus is under root 2 beta by capital. In the graph, we can represent it as this. So this is the position for omega plus. This is the minimum value of the optical vibrations that can be excited in a one-dimensional diatomic chain, which is root over 2 beta by small m. And the maximum value of acoustic vibrations that can be excited in a diatomic chain of atoms is root over 2 beta by capital M. Also to point out that at these points, the curve is parallel to the k-axis, which means that vibrations lead to standing waves, or the vibrations at these ends are called normal modes of vibrations. Now if you see, since small m and capital M are different, so there exists a band of frequencies which lie between a frequency band omega, which is greater than omega minus and less than omega plus. Within this band, no wave-like solutions are possible, which means that it is not possible to excite vibrations in a diatomic lattice at frequencies which lie inside this band. This band is termed as the forbidden band, and the existence of forbidden band is the characteristic feature of elastic waves in case of linear diatomic chain of atoms. Obviously, if capital M and small m are same, in that case the forbidden gap will vanish and the minimum frequency of the optical vibrations coincides or overlaps with the maximum frequency of acoustic vibrations. So if you compile the outcomes of the description made so far, the first outcome would be that the description curve repeats itself at regular intervals. We have seen that the pattern of the dispersion curve for a diatomic chain of atoms repeats itself at regular intervals, just like the dispersion relation or the dispersion curve of a monoatomic chain of atoms. We know that the pattern within one Brillouin zone is repeated in subsequent zones. It could be seen that in case of a diatomic chain of atoms, the allowed frequency range of propagation is split into two branches. One is the optical branch, the upper branch, and the lower branch is called the acoustical branch or acoustic branch. The acoustical branch is similar to the dispersion curve of a monoatomic chain of atoms. Now there exists a band of frequency below the lower limit of the optical branch and above the upper limit of the acoustical branch. There exists a band of frequency within which no lattice vibrations are possible. So this band of frequency between the two branches for which the lattice vibrations are ceased completely is termed as the forbidden band. This is the forbidden band. The width of the band depends on the ratio of the masses of the two atoms, that is capital M by small m. Larger the value of the capital M by small m ratio, greater will be the width of the forbidden band. So if you could see in the dispersion relation curve, the minimum frequency limit of the optical vibrations is root 2 beta by small m, and the maximum value of the frequency of vibrations of the acoustical branch is root 2 beta by capital M. So if we take the ratio of omega plus by omega minus, then we get this to be root 2 beta by small m divided by root 2 beta by capital M. So this 2 beta cancels. So this becomes root over capital M by small m. So thus, greater the value of this ratio capital M by small m, larger will be the deviation between omega plus and omega minus, and hence broader will be the forbidden band. The regime, that is between k values plus minus pi by 2a, is the first Brillouin zone. And these lines in 2 dimensions, which acts as planes in 3 dimensions at k values plus minus pi by 2a, are called Bragg planes. If you see the lattice vibrations both in optical branch and the acoustical branch, they become stationary at these k values, that is plus minus pi by 2a and subsequent Bragg planes. So what does it mean? It means that at these k values, the energy is not propagated through the lattice, and hence, in other words, we can say they are absorbed within the lattice. If you find the smallest possible wavelength that can be absorbed by a diatomic chain, that will be given by lambda, that is equals to 2 pi by k, and k, where first standing waves patterns are formed, is at pi by 2a. So we replace k by pi by 2a and we are getting it to be 4a. That is the smallest possible wavelength that can be absorbed by a diatomic chain is when lambda is equal to 4 times a, where a is the lattice constant. If you look into the dispersion curve of the diatomic chain, you can see that the frequency of vibrations varies from 0 to a maximum value of root over 2 beta 1 by small m plus 1 by capital M. And that is what is mentioned over here. The frequency range in the diatomic chain varies between 0, root over 2 beta times 1 by small m plus 1 by capital M. Now, if you increase the heavier mass, 1 by m becomes smaller and smaller. The optical branch flattens. And this value, the maximum value of the acoustical branch, which is 2 beta by capital M, this decreases, which means that the acoustical branch shifts downwards. Now, for a special case where capital M, that is the heavier mass, tends to infinity, or we can say the heavier mass becomes much heavier than the smaller counterpart, in that case 1 by capital M can be regarded as 0. This shifts to root over 2 beta by small m. So this maximum value comes down here, which means that the optical branch becomes parallel to the k-axis, whereas this omega minus maximum value becomes 0, which means that the acoustical branch coincides with the k-axis. So as the heavier mass capital M increases, the optical branch flattens and the acoustical branch shifts downwards. For a special case, when M tends to infinity, the acoustical branch coincides with the k-axis and the optical branch becomes parallel to the k-axis at a value root 2 beta by small m. What does it mean? It means that under such a condition, all the atoms vibrate with the same frequency, that is root 2 beta by m. This frequency can be regarded as the natural frequency of the system. If we look into the physical meaning of such a description, we could say that every atom in the lattice behaves as if it is completely free and isolated from its neighbors. It oscillates with its natural frequency, which is root over 2 beta by small m, and it is this concept which Einstein used to develop the theory of specific heat capacity of solids. Now, on the other hand, if you consider decreasing the lighter mass small m, what will happen? If small m decreases, 1 by small m increases, which means this value will shift upward. Similarly, the minimum value of the optical branch, minimum frequency value of the optical branch, which is root over 2 beta by small m, will also shift upward, and the frequency range of the acoustical branch remains unaffected. As m tends to 0, this omega plus becomes infinite. Similarly, this value also becomes infinite, which means the optical branch disappears. The lattice then appears to be a monoatomic chain with lattice constant 2a. Now, if we try to plot the amplitude ratio, the vibrational amplitude ratio of these two atoms as a function of k vector k for both the optical as well as acoustical branches, we get a plot something like this. Now, for k tending to plus minus 2a, that is at the Bragg planes of the first Brillouin zone, this capital B by A will become 0 for the optical branch and will become infinite for the acoustical branch. We know capital B is the amplitude of vibration of the heavier mass, that is capital M, and small capital A is the amplitude of vibration of the smaller mass, small m. Now, if I am saying B by A is 0, which means capital B is 0, physically it means that for the optical branch, all the heavier atoms with mass capital M are at rest. And in the same condition, for the acoustical branch, B by A is infinity, which means A is 0. That means in the acoustical branch, all the lighter atoms of mass small m are at rest. We can evaluate it further in the graph. So you see the main question is how can we draw this graph? So if you remember, while deriving the dispersion relation for a diatomic chain of atoms, we come across a set of linear homogeneous equations in terms of capital B and capital A. These are equation 3 and equation 4 and are represented as follows. So if you work out with this two expressions, we can use these two expressions to plot this graph. So if I take this expression on the other side, we get it this. Similarly, if I take it on the other side, we get it here, and there's one negative sign, this negative sign cancels. So I can write B by A from this expression as 2 beta minus small m omega square divided by 2 beta cos Ka, and from this expression B by A would be 2 beta cos Ka divided by 2 beta minus capital M omega square. Now we know the dispersion relation for a diatomic chain is expressed like this. If we want to get this plot for the acoustical branch, we have to take omega minus, that is the dispersion relation for the acoustical branch, and put that value here in this place. If we replace this omega square with omega minus square, the ratio of B by A we'll get is for the acoustical branch. This is the plot. If you put omega minus here or here and plot it, you will get this kind of. Now let us evaluate the case which we had just discussed now, that is when K is plus minus 2A. You can say when K is plus minus 2A, B by A ratio shoots to infinity. Now we know from the dispersion relation curve that at K equal to plus minus pi by 2A, omega minus attains a maximum value which is 2 beta by capital M. If you put this value here as 2 beta by capital M, and this at K equal to plus minus 2A, this cos K will become 0. So this term will become 0 here, and here if I cancel this capital M, this also becomes 0. So this term is an indeterminate form. From this we cannot attain a value for B by A. Let us try this one. This becomes 0 here because cos K is 0, and this is 2 beta minus small m times 2 beta by capital M. That means here it is, this exists and this leads to a value called infinity, and that is what is being shown over here, that for K equal to plus minus pi by 2A, omega minus shoots to infinity. For another condition, when K is 0, we know that omega minus is 0. So if we put K equal to 0, this becomes 1. So if we put K equal to 0, this becomes 1. So this will be 2 beta, and then this factor will be 2 beta minus this value, that is this factor becomes 0. So this will become 1. Using this expression also, this factor is 1 and this factor is 0. So there also B by A becomes equal to 1. So that is reflected over here. It is at K equal to 0, B by A for the acoustical branch is equal to 1. And if you plot for all other values of K, the curve appears to be like this, the blue one. Now for the optical branch, if we retain only the positive sign here in the dispersion relation, we get an expression for omega plus, and omega plus square can be expressed as this. If we replace this omega with omega plus, then we get a B by A ratio for the optical branch. And we have seen earlier that for K equal to plus minus pi by 2A, this B by A ratio is 0. Let us evaluate this. So when K is plus minus pi by 2A, we know omega plus is root over 2 beta by small m. So if I cos K here is 0, so this will be 2 beta into 0, which is 0, and then here it will be 2 beta minus capital M times 2 beta by small m. This will become 0, whereas in this case the denominator is 0 and here it becomes 0, so this takes a 0 by 0 form, so we will not consider this expression here. So B by A for the optical branch is 0 under the condition when K is plus minus pi by 2. For the case when K is equal to 0, we know that omega plus is root over 2 beta times 1 by small m plus 1 by capital M. So if we put this expression now, when K is 0, cos K is 1 here, so I replace it with 1. Here also it is 1. So if I take this expression, this will be 2 beta here, and this will be 2 beta minus capital M, and here we can write 2 beta times 1 by small m plus 1 by capital M. If we evaluate it further, I can take this 2 beta common. So this 2 beta, this 2 beta, and this 2 beta cancels. So we are left up with 1 divided by 1 minus, here it is capital M by small m, here it is 1. So this one and this one cancels. So we are getting it to be minus small m by capital M. You get a similar expression if you use this one. So here, when k is 0, the value is minus small m by capital M. So these are the possible outcomes of the description made so far. But from all such discussions also, we are not in a position to visualize the optical and acoustical vibrations within a lattice. If we got the privilege to observe the optical and acoustical branches within a lattice, we are not in a position to differentiate or to say which one is the optical vibration and which one is the acoustical vibration. The maximum information we are having at this point of time is that at any wave number or wavelength, we could have only acoustical vibrations in case of monoatomic chain of atoms, while for every wave number, we can have both optical as well as acoustical vibrations in a diatomic chain of atoms. And the only differentiating parameter we know at this point of time is at any wavelength or wave number, the optical vibrations will have higher frequency as compared to the acoustical vibrations. So let us now try to understand the nature of vibrations in optical and acoustical branches within a lattice, in this case a diatomic chain of atoms. Using again the two linear homogeneous equations in terms of capital A and capital B, that is equation number 3 and equation number 4, we get this. Now for the optical branch, we know that at Ka equal to 0, the optical branch exists. So when we put Ka equal to 0, cos Ka will become 1. So this term here and this term will become 1. So under this condition, equation 3 will take the form as this. We put this cos Ka term 1. So it will be 2 beta minus m omega square within bracket times A minus 2 beta B, that is equal to 0. Similarly, the fourth equation takes the form minus 2 beta A. This cos Ka terms becomes 1, and within bracket 2 beta minus capital M omega square times B, that is equal to 0. Now bringing the 2 beta terms together, we get, so here it is 2 beta A minus 2 beta B, and this term on the other side of this equal to sign, it is m omega square A. So finally, we could write omega square by 2 beta, this omega square, and 2 beta we take it on this side, then it will be A minus B divided by small m times A, which is written over here. Similarly, with this second equation, again bringing the beta terms together, and then we can get another expression for omega square by 2 beta, that is equal to minus A minus B divided by capital MB. Now we can equate both these terms. So equating, we get this A minus B and A minus B can be cancelled here. So it will be 1 by small m times capital A, that is equal to minus 1 by capital M times capital B, from which we get A by B is equal to minus capital M by small m. Now this is a very important relation from which we could extract some information. The first information is that since capital M is greater than small m, the vibrational amplitude of the atom having smaller mass is more as compared to the vibrational amplitude of the atom having heavier mass. So the amplitude of vibration are inversely proportional to their masses. So the center of mass of the unit cell remains unchanged, which means that in optical vibrations, the center of mass of the unit cell doesn't change. It remains fixed. The second is, since there is a negative sign in this expression, which means the amplitude of vibrations of these two atoms are opposite at any instant of time. So the two atoms always move in opposite directions. If in any case capital M is equal to small m, then A by B will be equal to minus 1, which means that if their masses are equal, the atoms always move in opposite directions, but in this time with equal amplitude. So in optical vibrations, the two neighboring atoms move in opposite direction and their amplitudes are inversely proportional to their masses, so that the center of mass of the unit cell remains unchanged. Coming to acoustical vibrations, we know the acoustical vibration doesn't exist at K equal to 0. So we will consider the case for low values of Ka, that is Ka tending to 0. We can expand cos Ka binomially and retain only the first two terms. The higher order terms are neglected because Ka is is very small. So if we replace this Ka with this expression, the equation 3 takes the form. So this cos Ka has been replaced as 1 minus K square A square by 2, and this term is 2 beta B is here. And the fourth term here, that is minus 2 beta A, in place of cos K, we have written 1 minus K square A square by 2, and then this term has been copied as it is, so it is plus 2 beta minus m omega square B. Taking this term, this is minus m omega square A, and bringing the beta terms on the other side of the equal to sign, it will be 2 beta B 1 minus K square A square by 2, and this one is on the, if we bring it on the other side, it will become minus 2 beta A. Similarly, doing the same exercise with this equation, we can write minus capital M omega square B on this side, and bringing this term on the other side of the equal to sign, it becomes minus becomes positive, so it is plus 2 beta A 1 minus K square A square by 2, and this term is plus 2 beta B here. Taking it on the other side, it becomes minus 2 beta B. If you add both these equations, we can take minus omega square common. It will be small m times A plus capital M times B, and that will be equal to minus, here you could see this term 2 beta B, this term cancels with this term, and this term cancels with this term. So we get a negative sign here, and this 2 cancels, this 2 cancels. So it is minus K square A square beta A plus B. And if we want to get information about the acoustical branch, we know that for such a case, the frequency of acoustical vibrations omega minus is Ka times root over 2 beta by small m plus capital M for small values of K. We replace omega here with this term. So if we do so, we can write here omega square as K square A square. Then here it is 2 beta divided by small m plus capital M. This term remains as it is, and the other term also remains as it is. Now this beta cancels, this K square cancels, this A square cancels, the negative sign cancels. So what we are left up with, this is 2 times small m A plus capital M B, and then this we take it on the other side, so it will be small m plus capital M times capital A plus capital B. Now we expand this, then what we get is 2ma plus 2mb is equal to small m capital A plus small m capital B plus capital M capital A plus capital M capital B. Here also 1 ma term cancels, and 1 m and 1 mb terms cancels. So this becomes small m times capital A plus capital M times capital B, that is equals to capital M times capital A plus small m times capital B. So we bring the A and B terms together. It is small m minus capital M whole times A, and it's small m minus capital M times B. So we cancel it. We get A by B is equal to 1. So with this also we get two very important information. Irrespective of the fact that both the atoms are having different masses in a diatomic chain of atoms, amplitude of vibrations, they are same. And since it is positive, these two atoms move in the same direction. As a result of which, in such kind of vibrations, there will be a movement of their center of mass. So the information which we get here in case of acoustical vibrations is the two atoms of different masses move in the same direction and with the same amplitude, resulting in the movement of their center of masses. So I tried to visualize all the various modes of vibrations which are possible in a diatomic chain of atoms. So from our discussion made so far, we know that the two atoms of different masses in a diatomic chain, when forced to vibrate, then the acoustic vibrations in the longitudinal mode, the two atoms move in the same direction with the same amplitude, and the movement leads to the movement of the center of mass of the unit cell. In case of the diatomic lattice, these two atoms comprises a unit cell. You can see here that the center of mass of the unit cell seems moving. This is the representation, a GIF representation of how such longitudinal vibrations inside or within a diatomic chain of atoms comprising of these red and blue atoms would look like under the following conditions. Now, if we move to optical vibrations under the similar conditions, you would see the vibrations here changes like this. And here the two atoms move in opposite direction and their amplitudes are inversely proportional to their masses. So the center of mass seems to be constant. So clearly there is a difference between the acoustic vibrations in the longitudinal mode and the optical vibrations in the same mode. The difference between acoustic and optical modes is visualized in a better manner in transverse mode, and hence in most of the books such a representation is given in a transverse mode, although our calculations are for longitudinal mode. In transverse mode, if you see, the acoustic vibrations would look something like this. So the concept here also remains the same. The atoms move in the same direction with the same amplitude, comprising of a wave like this. However, when we shift to optical modes, the vibrations of these two atoms are in the opposite sense or opposite direction, so leading to a vibration something like this. So clearly the mode of vibrations are different, and obviously here in case of optical mode, the frequency of vibration is more as compared to what we have in under similar conditions in acoustic mode. Now, if we compile the properties of acoustical vibrations or acoustical phonons, which are nothing but the quantum of energy or the unit of energy associated with these acoustical vibrations, we can write that these vibrations are nothing but collective in-phase vibrations of atoms in the crystal lattice, where the neighboring atoms vibrate in the same phase. They have a zero frequency at the center of the Brillouin zone. Acoustic vibrations in the low wavelength limit, that is for small k values, approaches the speed of sound, and that is why they are termed as sound waves or acoustical waves. These acoustical vibrations are significantly responsible for the thermal conductivity of solids. These acoustical phonons, they are involved in electron phonon scattering, which leads to electrical resistivity in materials. Now, these acoustical vibrations are classified into various categories. If the atoms vibrate parallel to the direction of wave propagation, they are termed as longitudinal acoustic vibrations, also termed as LA mode. If the atoms vibrate perpendicular to the direction of wave propagation, then they are termed as transverse acoustic mode or TA mode. And in some cases, particularly in 2D materials, when atoms vibrate perpendicular to the plane of the lattice, they are termed as out of plane acoustic mode or flexural mode or ZA mode. Similarly, the optical vibrations or the optical phonons, they correspond to out of phase vibrations of adjacent atoms within the unit cell. They have a non-zero frequency at the center of the Brillouin zone. Optical vibrations are excited by a force that makes the neighboring atoms move in the opposite direction. Normally, optical radiations induce these kind of vibrations in a crystal, and that is why they are termed as optical vibrations. For instance, in ionic crystals like sodium chloride, when excited by infrared radiation, which is an electromagnetic wave, the electric field of this infrared radiation will move every positive sodium ion in the direction of the field, while every negative chloride ion in the direction opposite to that of the field, leading to optical vibrations. Now, these vibrations play a very significant role in light matter interactions like infrared absorption or Raman scattering. Crystals which involve direct interaction of optical phonons with light are infrared active, while those involving indirect interaction of optical phonons with light is Raman active. Now, they are also classified into various categories. Optical vibrations are classified into different types. Vibrations parallel to the direction of wave propagation are termed as longitudinal optical mode or LO mode. Vibrations perpendicular to the direction of wave propagation are termed as transverse optical or TO mode. And in 2D materials, vibrations perpendicular to the lattice plane are termed as out of plane optical mode or ZO mode. So let us stop here. In my next lecture, I'll show you that the dispersion relation or the phonon spectra of the systems which we have dealt so far, that is the monoatomic and diatomic chain, are among the simplest cases. The phonon spectra of real 2D and 3D materials like graphene, gallium arsenide, molybdenum disulfide, and many more are far more complex. I'll try to explain how to predict the number of phonon branches in such complex systems. So see you in the next lecture. If you like this video, press the like button, subscribe this channel, and press the bell icon so that you don't miss any notifications. Thank you.